In this video, I want to solve a problem from a university entrance exam in my country. What is the quotient group G over H isomorphic to? The first step is finding the order of our quotient group. You can simply see that the order of G is equal to 2 times 8, which is equal to 16. Now we have to find the order of the subgroup H that is generated by 0, 4, and 1, 2. Because 1, 2 is one of the generators of H, so H includes all the powers of 1, 2. So first we calculate all the powers of 1, 2. 1, 2 to the second power is equal to 1, 2 plus 1, 2. We add the first component mod 2 and we get 0. 1 plus 1 equals 2, 2 mod 2 equals 0. We add the second component mod 8, 2 plus 2 equals 4. Now we calculate 1, 2 to the third power, so it is equal to 1, 2 plus 0, 4. Again, we add the first component mod 2 and we get 1. And we add the second component mod 8 and we get 6. Then we calculate 1, 2 to the fourth power, which is equal to 1, 2 plus 1, 6. And then we get 0. And after adding the second component, 2 plus 6 is 8. And 8 mod 8 is 0. Okay, that's it. So here is the group H. It has all the powers of 1, 2. Here we have 1, 2, 1, 2 to the second power, which is equal to 0, 4, 1, 2 to the third power, which is equal to 0, 6, and 1, 2 to the fourth power, which is the identity element of the group. And as you see, 0, 4 is just 1, 2 to the second order. So here writing this element is redundant, and we can only write H is generated by 1, 2. So H is a group of order 4 and is generated by a single element. So it is a cyclic group of order 4, which is isomorphic to the group Z4. That's it. Now we can simply find the order of the quotient group G over H. So the order of G over H is equal to the order of G divided by the order of H. The order of G is 16 and the order of H, as we calculated, is equal to 4. So the order of our quotient group is 4. So we know that we have two groups of order 4 up to isomorphism. First is the cyclic group of order 4, and second is the Klein 4 group Z2 cross Z2. All right, now we have to determine which group our quotient group is isomorphic to. If we find an element of order 4, we can conclude that our quotient group is isomorphic to C4. But if all elements that we calculate are either of order 1 or 2, we can conclude that it is isomorphic to Z2 cross Z2. Okay. We know that elements of our quotient group are the form GH, where G belongs to G. And the identity element in our quotient group is just the identity coset H. And I want to remind you that AH, the coset AH, equals H if and only if A belongs to H. We want to use this in our example or in finding the order of elements in our group. Let's, for example, consider the coset 1, 1H and find the order of this coset. We know that it is not equal to H because 1, 1 doesn't belong to H. Here we said that AH equals H if and only if A belongs to H. So 1, 1H is not equal to H simply because 1, 1 doesn't belong to H. Here we calculated the group H, all the elements, and we need it here. So let me copy this group. Okay. Okay, it's our group. We say that 1, 1 doesn't belong to H. So 1, 1H is not equal to the identity element. Now let's calculate 1, 1 to the second power. I mean 1, 1H to the second power. We know that it is equal to 1, 1 to the second power H. And let's calculate it. It's 1, 1 plus 1, 1H. Again, we add first components mod, because our group G is Z2 cross Z8. We add the first components mod 2. 1 plus 1 is 2, mod 2 is equal to 0. And we add the second components mod 2. So we see that 0, 2 doesn't belong to H either. So it's not equal to H. So the order of 1, 1H is not 2. Now we calculate this quotient to the third power. 1, 1H to the third power is equal to 1, 1 to the third power H. And let's calculate 1, 1 to the third power is 1, 1 plus 0, 2. And we add the first components mod 2, we get 1, and second components mod 8, we get 3. So as you see, 1, 3 doesn't belong to H. So 1, 3H, this quotient is not equal to H. It's not equal to the identity element. So the order of 1, 1H is not 3. Now we calculate 1, 1H to the fourth power, which is equal to 1, 1 to the fourth power H. And this is equal to 1, 1 plus 1, 3H, which is equal to 0, 0. Sorry, I made a mistake. If we add the first components, we get 0, mod 2. And then we add the second components, 1 plus 3 is 4 mod 8. And as you see, 0, 4 belongs to H. So 0, 4H equals H or the identity quotient. So we see that this quotient to the fourth power equals the identity element. So we conclude that the order of 1, 1H is equal to 4. And we also prove that the order of G over H, our quotient group, is equal to 4. So we have a quotient group of order 4, which has an element of order 4. So it is equal to the cyclic group of order 4. And here we see that the correct answer is option 4, because we proved that H is equal to, in fact, H is isomorphic to Z4, and our quotient group is isomorphic to Z4 too. So this is the correct answer. Thanks for watching the video.